this is Katrina, and our design pattern presentation is on the strategy design pattern. So here's a little bit of an overview of the pattern. So the strategy design pattern is a pattern that enables the behavior of an object to be determined at runtime. The dynamic assignment of behavior has a number of implications for developers and clients. More on this later. You'll hear from Max about that. The strategy design pattern falls under the category of behavioral design patterns, which primarily deal with algorithms and the assignment of responsibilities among objects. At its core, the strategy pattern facilitates the definition of a family of interchangeable algorithms. Each algorithm in the family is implemented as a discrete and standalone unit. This design pattern promotes modularity and flexibility, as it allows the algorithms to substitute one another with no change in core functionality on the client's end. Now, I do feel like it's worth noting that by core functionality, what I mean is like the program will still carry out its intended function or its objective, but it's just the way that it does it will differ. And that is usually to either optimize the runtime or to optimize based on the factors that the user requests, which we'll see an example of soon. Alright, so actually here it is. So a real-world example of the strategy design pattern in action is in navigation apps. So think Google Maps, Apple Maps, Waze, and anything else like that. So let's suppose that I want to travel from point A, which is the Union, to point B, which is the Folsom Library, on the map shown below. So here's a better view of the map. This is obviously the RPI campus, and let's just assume that I'm trying to get from point A to point B. So if I were to use a navigation app like Google Maps, for instance, I could specify various factors that will dictate which algorithm the application chooses to calculate the path between point A and point B at runtime. So notably, again, the core functionality remains the same, although the underlying program may employ a different strategy based on the travel factors I choose to specify. So like the method of travel, like whether I go by car or walking, on bike, etc. Or if I want to make specific stops along the way between point A and point B, I will still end up at point B. That's kind of paramount. So to better demonstrate how the strategy design pattern functions, let's actually visualize this example using the map. So let's suppose that I specified that I would be walking between point A and B. So the following path is calculated, and this is actually from Google Maps. Like, this is the path that it gave me. So as you'll notice on the right-hand side, for pedestrians, it optimizes distance, scenery, sidewalk traffic, safety, and extreme elevation changes. And based on whether or not it has a plus or minus sign next to it, it just demonstrates whether or not that factor is being minimized or maximized. So for example, if you're walking, you would want your distance to walk to be minimized, so you don't have to exercise as hard. Or in terms of safety, you would want that to be maximized, so it won't route you through like high crime rate areas. So here's what it looks like if I specify that I will be biking. And as you can see, the path has changed, but I'm still moving from point A to point B. And here, the factors that it optimizes are slightly different, but they are very similar to pedestrian because it's a very similar mode of travel. And now, if I wanted to stop at Big Apple on my way from point A to point B, this is the map this is the path that Google Maps calculated for me. And again, it's optimizing for, I believe it's also on bicycle. It's optimizing for the factors shown on this slide. Alright, in terms of the structure, the strategy pattern is made up of three main components. Those are the context, the strategy interface, and the concrete strategies. So the context is the class that uses a strategy, or more specifically, it maintains a reference to a strategy object. Generally, the context has a method to set the strategy dynamically at runtime. The strategy interface defines the behavior of all the supported algorithms that we talked about prior. The context uses said interface to call the algorithm defined by a concrete strategy, which are the classes and functions that implement the strategy interface. So each concrete strategy implements an algorithm, and those belong to the family. using the strategy interface. So that's a little confusing. So to give you a better idea of how each of the components relate to one another, look at the diagram right here. And I modeled it after the example that I showed earlier. So this is a UML diagram, but in the context of the example I just showed. So here, context would be the Google Maps interface right here. The strategy interface would be the underlying algorithm picker. So that's right there. And concrete strategies, which I just shortened to constrat, are all of the algorithms. So we've got a walking algorithm, biking algorithm, pit stop algorithm, and in reality, there are many, many more, but this is just for our. And this can be generalized into a more generic UML diagram of the strategy design pattern, which is shown here on the right. Um, and as a reminder, the context class has a reference to a strategy object, which is set either through its constructor or setter method. The strategy interface will define the method algorithm, which will be implemented by the concrete strategies at the bottom. And Constrat 1, Constrat 2, and Constrat 3 are the different implementations of the strategy interface, which each provide different behaviors and algorithms.
So now we're going into the actual implementation details. As you heard, the chosen algorithm will be accessed through a shared interface, not showing the internals of that algorithm. A program may choose the algorithm based on different conditions encountered at runtime context. They'll still be called with the same methods, regardless of which actual algorithm is being chosen. So this is importantly utilizing the principle of abstraction. Without it, trying to switch which algorithm is being used is going to become funky and confusing. You can imagine there's going to be a mess of code everywhere with if-else's and then sorting algorithms implemented in the middle of the code, and it's just going to look really off if that's not what your uh, class, for example, is completely about. The context, not knowing the exact implementation of the algorithms selecting is important to keep these two different classes from being too intertwined. Here are the consequences of the strategy design pattern. There are many pros and negatives depending on the context in which you're trying to use this design pattern. There's times when it's going to be appropriate to use it, and times when it's going to be inappropriate to use it. For programs with a dynamic context, where there's going to be many conditions determining the algorithm used, and these conditions are going to be frequently changing, this would be a good time to use the strategy design pattern, as the abstraction of it will simplify the requirements of the client who's calling the algorithms. They won't need to worry about the internal implementation of those algorithms at that point, and the client won't be able to see that. The logic of different algorithms is separated from the caller, and that's going to reduce the unnecessary dependencies between the caller of that algorithm and the actual implementation of the algorithm itself, sticking to that single rule of implementation. This also follows the principles of being open for extension but closed for modification, as adding new algorithms is simple since this existing interface defines the rules for new algorithms, and creating a new algorithm simply follows that interface and doesn't require modification of the original caller since it can just be inserted new and is decoupled from that caller. However, there are times when the strategy design pattern is not appropriate to use. For a simple context, a program that doesn't require much switching of algorithms, if at all, the added implementation and abstraction of this design pattern can end up being more confusing than simply without it. For a program that's really simple, or it only needs one algorithm or maybe two algorithms, it might not make sense for the confusion of different classes and different uh, algorithm objects when really it's not going to be all that necessary. Additionally, since the algorithm is going to be chosen at runtime, this can provide some overhead which could otherwise be avoided. If you have a way to determine which algorithm is going to be used at compile time, then it's going to be much quicker than checking a condition and running that running that program at runtime. Here is a context class in Java that has a sorting algorithm, sets a sorting strategy, and just performs that sort. It's a pretty basic class. So we have an array of 1,000 random integers, and we have a context, and we're given this quicksort algorithm to this context. And we set, if the length is over 10,000, then we are going to switch it to a merge sort. Let's just say theoretically here that merge sort will be more efficient for a larger array, but quicksort will be more efficient for a smaller array. So we perform the sort, and now we have a new array of 1,000,000. And again, we check to see that the length is greater than 10,000, and we switch it to a merge sort now and perform the sort. The client is going to be calling the sort through the same interface, uh, but the actual implementation inside is going to be different depending on the conditions of this context. If we look at the interface, it's pretty simple. We just have one method that says something that implements a sort algorithm just needs to implement sort or int array, and nothing about its actual internals. We look at merge sort, and we have sort, merge sort, and here's where this abstraction comes to play. Merge sort is implemented recursively here, so it has several arguments, and not just the one array argument that's being passed in. So while the client only sees sort array, inside merge sort is actually several arguments and several methods. This is all abstracted. The same thing applies to quicksort. This quicksort is also a recursive implementation, and such has several arguments, not just the argument array, but again, because of this interface, the client only needs to interact with this sort function and not the internal implementation, leading to a universal such interface here. As you can see, algorithm.sort array. It's the same no matter what strategy is being chosen at this point.
All right, thank you for tuning into our presentation. We hope that you have a better understanding of the strategy design pattern now, and feel free to let us know if you have any questions. Thank you.